Hi everyone, this is Alan, and today we're going to be talking about Calculus 1 in a nutshell. So let's get right into this. So the main topics in Calculus 1 that we would be talking about is differentiation, complex limit, and integration. There are a lot more units or other components that are part of Calculus 1, but these are the most important. So let's first start off with differentiation. So we'll be talking about what is a derivative, what are the main rules of differentiation, and how would we solve them. So let's first introduce by what is the true definition of the derivative. So as you can see here, it is the change of y in respect to x. So what does this all mean for us? Well, as you can see, the secant line is between 2 points, point P and point Q. And what we're trying to find is basically the slope in between these 2 points. Now you may think it's like in slope-intercept form where you take y2 minus y1 over x2 minus x1, which is similar to what this is, but the thing is that there are many slopes in this curve. So if we take the slope of P, there's going to be a specific slope, and then if we take a slope of Q, there's going to be a specific slope. And that slope is better known as the tangent line. So let's try and draw it. So at point Q, you could see, I'm going to draw a red line here. It's not perfect, but you can kind of see on where the point would be around there, and then you have point Q, which you're going to have a tangent line right here. So you could see the slopes are relatively different. And what we're trying to do is that there are different rules by using differentiation in order to determine those slopes at that particular point. So let's talk about what these rules are. So as you can see, there are 4 main rules towards differentiation. And the first rule is actually one of the most commonly used rules when doing the derivative, which is known as the power rule. And then we move on into the quotient rule, which is where you have the function of x all over g of x, and then you take the derivative of f multiplied by the lower or the denominator minus f of x and take the derivative of g of x all over g of x squared. The product rule is very similar to the quotient rule. Instead, it only focuses on the numerator, and instead of the subtraction sign, you have the plus sign. And then you have the chain rule, which follows as f of g of x. You do the derivative of the outside function, and then you multiply by the derivative of the inside function. So these are some basic rules that you would have to know in order to differentiate. So let's get right into a few problems. So as you can see, for the very first one, we would have to use the power rule. And from that, you could see that 3 multiplied into 3 would make it 9. And then you would subtract 1 based on the rule. So you would have 9x squared. And then you would have that exponent of 1, x to the power of 1, multiplying to that negative 17. And then it would subtract 1, so that would become 0. So x to the power 0 is 1. So then you would have negative 17. And then the 4 is a constant. What happens with the constant? It equals 0, so it doesn't pertain to this. So that would be our final answer. Then we move on into the quotient rule. So this is going to be a long one right here. So let's try it. So if we have d of x, this is the best notation for doing the derivative of f of x, the power of 3 plus 2, multiply this entire expression by the lower, which is 17x plus 16 minus, and then you have 4x in power of 3 plus 2, and then you take the derivative of the lower, which is 17x plus 16, and that is going to be, the entire thing is going to be under 17x plus 16 squared. So once you do the derivative of the first one, which is f of x to the power of 3, which is going to be 12x squared. The 2 cancels out, so you would multiply this expression by 17x plus 16. Subtract that with 4x in power of 3 plus 2. And then the derivative of 17x plus 16 is going to be 17 all over 17x plus 16 squared. So then if you were to simplify this all, you would then have 136x cubed plus 192x squared minus 34 all over 17x plus 16 squared. And that would be your final answer for the second one. So then we will then have to move on into the third one, which utilizes the product rule. So let's get started with that. So with the product rule, we have to take d of dx. We know that f of x is 4x multiplied by 6x squared plus 5 plus 4x times the derivative of the inside function, or g of x, of 6x squared plus 5. So once we simplify this, we will have 4 multiplied by 6x squared plus 5 plus 4x multiplied by 12x. So then once you simplify this all down, you will then have 24x squared plus 20 plus 48x squared, which you can then simplify it more to 72x squared plus 20. So that is your derivative for the third one. The fourth one, we will have to use the chain rule, and we will utilize u substitution. So since the inner function is 3x to the power 7 plus 36, we're going to replace that with u. And u substitution is going to be a big part in calculus. So let's do u substitution here. So d of dx, or the derivative of 6u in power 4 multiplied by the derivative of the inside function, which is 3x in power 7 plus 36, right? So then we reduce this to 24u in power of 3 multiplied by the derivative here, which is 21x in power 6. And then we replace that u component with our original function. So that is 24, not 34. And then 3x to the power 7 plus 36 in power of 3 multiplied by 21x in power of 6. And you can reduce that even more. So the final answer would be 104 x in power of 6 multiplied by 3x to the 7th plus 36 in power of 3. So that would be your answer for the fourth one. Now this one, the bonus one, is a little bit interesting because we could do the quotient rule, but there is a faster way in order to solve this problem. So let me just write it down here again. So if we have d of dx minus 2x to the fourth, you can rewrite this expression. So d of dx is negative 2x and negative 4. You can rewrite this expression and it would still be the same thing because 1 over x over 4 is the same as x in power of negative 4th. So once we do the derivative, we just use the power rule. So negative 2 times negative 4 is 8. and then you have to subtract 1, which is x and negative 5, right? So our final answer, if you want to put it in this notation, you would have 8 all over x in power 5. Whoops. And that would be the answer for that one. So then we move on into more complex derivative rules. And you can see there are a lot. And there are trig. You have trig properties. You have inverse trig properties. And you also have exponential properties. So let's get into a few problems that implement those. So in the first one, you can see we have to find the derivative of sine of 5x plus 3 all over the natural log of x. So in order to solve this particular problem, we will have to use the quotient rule. So this is going to be a relatively long one. So we're going to do like this. So the derivative of sine of 5x plus 3, we're just going to bracket it so it would be a lot clearer, multiplied by the natural log of x minus sine of 5x plus 3, which is bracket that just in case, and then the derivative of the natural log of x all over the natural log of x squared. So the good thing about this problem is that it's pretty much almost done in the fact that simplifying it would take forever, but we could just leave it the way it will turn out. So what I mean by that is once we simplify the derivatives and we plug everything into each other, it should be complete. So if we do the derivative of sine of 5x, well, we will then have to use the chain rule. So we will have to find the derivative of the outside function, which is cosine of u, and that u is 5x, and then you will have to find the derivative of the inside function, which is 5. So I just multiply it on the outside. So your derivative of sine of 5x is 5 cosine of 5x. And then the constant 3 goes away. So you multiply by the natural log of x minus the sine of 5x plus 3 multiplied by the derivative of the natural log of x, which that is 1 over x based on the rules, all over natural log of x squared. Now, this would be the final answer, but you can simplify it a little bit more, but this is as far as I'm going to go for this video, in the fact that this could get complex with the simplifying. But this would be technically the final answer. Then we move on into the second equation. So for this, we will have to split up the differentiable. So you would have d of dx of 2x in power of 4 plus, 2x. And from there, you would then find the derivative of the first one being 8x in power of 3. And then this one is going to be a little tricky, because whenever from the properties that we have learned from the previous slide, you can see that right here, where we have to find the derivative of b of x, it equals b of x times the ln of b. So we will have to use this in this property right here. So we're going to do the natural log of 9 multiplied by 9 in the power of 2x. But since this is going to be u substitution here and the chain rule, you will multiply this entire expression by 2. So you could just leave this entire expression the way it is, but you can simplify it even further. So based on what we know about logs and exponents, you can change this up by having 9 turn into multiplied by 2, right? And then 9 2 of x. And then that 2 in the exponent can be brought to the outside. So by doing that, you're going to do 2 times 2 equals 4 ln of 3. So it's going to be 4 ln of 3 multiplied by 9 in power of 2x. And 9 in power of 2x can be simplified to 81 in power of x. So your final answer is going to be 8 in power of 8 of x of 3 plus 4, the natural log of 3, times 81x. So that's your answer for the second one. Now the third one is going to be a little interesting. So to start this off, we're going to identify what our u value is. And the reason why we would have to do this first is because it would be a lot easier in order to solve it. And also we would find our derivative, so we will have to use u substitution and the chain rule. So our u here is going to be the inside function underneath the radical. So it's going to be cosine of 7x plus x squared. So based on that, if you do the derivative of this function, let's do that right here, d of dx. We're going to simplify it. That's going to turn into negative 7 sine of 7x plus 2x. And that is based on the properties that we have learned and mastered from the previous slide. So based on that, now we can go back to the original function and do the derivative. So if we do this, square root of u, so what would the derivative be? Well, square root of u is the same thing as writing in u in power of 1/2. So if that's the case, and if you subtract 1, you're going to have negative 1/2. So negative 1/2, if you do the power rule, you're going to have 1/2 u in power of negative 1/2. Or better to write it in a radical form. So that would be your derivative. So now let's integrate our u back into our original function. So we'll plug in the expression of cosine of 7x plus x squared. And then don't forget the derivative because we have to use the chain rule. Multiply by negative sine of 7x plus 2. So once you figure this all out, your final answer, once you multiply it all through, is going to be negative sine of 7x plus 2 all over 2 square root cosine of 7x plus x squared. So that is your derivative for this one. So that is all we have for simplifying complex derivatives. So now we'll move on into complex limits. So we'll take a look at how hard the limits can potentially be and how we can use differentiation by using L'Hopital's rule in order to figure out the limit. So let's expand more on L'Hopital's rule. So what he has derived is that if your limit approaches a particular number, your f of x over g of x have to be 0 to 0 or infinity to infinity form. So I'll show you guys that in the following examples. So if that would be the case, then the rule complies. Well, if x approaches a particular number for a, then you would have to take the derivative of the top and the bottom function. So let's take a look at that. So as you can see, for these complex limits, we will be able to solve them pretty easily based on L'Hopital's rule. So based on what he had said, you got to make sure it's in 0, 0 form. The good thing is that it is already in 0, 0 form. So if we plug in 0 here, you get 0. But if you plug it in here, you get 0 as well. So this is in 0, 0 form. And then we'll move on into actually writing out the equation. So if we do the derivative of the top function, you get negative 4 sine of 4x all over 2x. Now I also want to mention a neat little property that you will use in calculus, which is as the limit approaches 0, sine of x over x approaches 1. So by just knowing that, you could see we can do a similar property to that. So if we take out the 4 out of the sine of 4x, you're going to have 4 multiplied by 4 sine of x over 2x equals negative 16 all over 2, which is negative 8. Because I took the sine of x all over x since the limit approaches 0 and it equates 1. So your limit for that one is negative 8. So now we'll move on into the second one. Now the second one's a little bit tricky, and there's always a trick to everything. As you can see, for this limit here, we have a natural log. Natural logs always stay in the numerator whenever you're doing complex limits. So in order to figure this one out, we have to move a term into a denominator so that we would have a form into infinity to infinity. So in order for that to be the case, what you will have to do is we'll move that x right here into the denominator. In order to do that, we'll do it 1 over x. So you will have the natural log of sine of 1 over x plus 1 all over 1 over x, because it's the same thing. If you do the reciprocal of that, you get x. So relatively speaking, this is the same thing. So based on this, this is going to be the 0 to 0 form. And how I know this is that as long as you plug infinity into here, you can plug in 1,000, 1,000,000, 1,000,000,000, or whatever. The bottom and the top are approaching 0, so they are both in 0, 0 form. So based on that, we can do L'Hopital's. So the derivative of the top function, we'll have to use the chain rule. It will be 1 all over sine of 1 over x plus 1 multiplied by the derivative of sine of 1 over x plus 1, which equals cosine of 1 over x, and then you have to multiply it by the inner function again, because sine has 1 over x. It's not just x itself. If it was x by itself, it'd be just cosine of x. But since we have an inner term, the derivative of 1 over x is negative 1 over x squared. You have to master that once you get more practice. And then the derivative is the same thing, so it would be negative 1 over x squared. Now you can also see that terms can cancel out here. So then what you would be left with is just the limit as x approaches infinity as cosine of 1 over x all over sine of 1 over x plus 1. So based on that, if we plug in infinity here, we get 0, right? So we get 0. And the cosine of 0 is 1. And if we plug in the sine of 0, we get 0, but it has an additional 1, so it would be 1. So your final answer is going to be 1. And then the third, we will have to do a bit of a different trick. So since cosine is in power of cosecant, in order to figure this one out, we will have to raise the entire function in power of e. Because what we will use is we will use this formula here. B of x equals e in power of x ln of b. So based on knowing that, we can rewrite this entire expression in e of the limit x approaches 0 of cosecant x times the natural log of cosine x. So by just knowing that, you can use El Hospitals, because as it approaches 0, it goes to infinity to infinity. So let's work on that. So if we have this, and we were to simplify this, we can have the natural log of cosine over x all over 1 over cosecant of x. So natural log would be 1 over cosine of x multiplied by negative sine of x all over cosine of x. And you could see that the cosines would cancel. So then what you'll be left with is negative sine of x, which equals 0 as it approaches 0. So our final function would be e in power of 0, which is just 1. So that is on how you would have to solve complex limits. And then last topic, we will have to move into integration. So integration is the antiderivative of a derivative. So you're basically going back to the original function. And then we will go on into the fundamental theorem of calculus. So here are some integration rules that you will have to know once you go into calculus. And the most common one is using the power rule, which is similar to the power rule of differentiation, but you will have to add instead of subtract 1, and then you will have to do it all over by the exponent plus 1. So let's take a look at a few examples for that. So for the first one, what you can do is we can use u substitution. So our u is going to be 15x minus 7, right? So we can rewrite this entire indefinite integral of 1 over u of du. So just by doing that, we can find the derivative of u. So du to dx is 15. So then that makes it du over 15 equals dx. So that 15 will be out in front here because constants or any kind of constant multiples will be pulled outside of the integral. So then you will have u, 1 over u. So just by doing that, The integral of 1 over u is the natural log of the absolute value of u. So we'll have 1 over 15 ln natural log plus c. Plus c is your main constant, and that will be used a lot whenever you're doing indefinite integrals. But when you're doing definite integrals, you don't need plus c because you're finding the area automatically. So we just plug the equation back into u. So 15x minus 7 plus c. So that would be your answer for the first one. The second one, we will have to use substitution. So we'll just do e in power of u, more so saying u is going to be x to the 6th. So if you do the derivative of that, du the dx is going to be 6x to the 5th. So then you would have du all over 6 equals x to the 5th dx. So as you can see, it is very similar because we have dx and we have x to the 5th. So just by doing that, we have actually made our problem a lot easier. So if we pull out 1 over 6, all we have to do is solve the integral of e to u dx. And for that, or more so that should be du, the integral of e in power of u is going to be e in power of u. So your final answer is going to be e in power of x into the power 6 all over 6 plus c. That's your answer. For the third one, we'll do u substitution again. So u equals 1 minus 6x in power of 6. So if we take the derivative of this, we will get negative 36 x in power of 5. So then just by doing that, du all over negative 36 is going to be x in power of 5 dx. So you can see that x to the 5 and dx are right there. So we can simplify this even more. So since there's a constant of 2, we'll put that outside of the integral. So you would have 2 times 1 over negative 36. We'll do the integral of 1 over the square root of u in du. So just by doing this, this turns into negative 1 over 18. And then the integral of this entire expression is going to be, you're going to have square root u in the numerator all over 1/2. That's just if you simplify it even farther once you solve the integral. This is the same as u in power of 1/2 all over 1/2. So the 1/2 goes directly into here, into the negative 1 over 18. So that turns in negative 1 over 9. And then the integral of square root of u. And you just plug in u into the original function. So your final answer is going to be negative u, or square root of 1 minus 6x squared all over 9 plus c. And that is your answer for that particular integral. Now we'll move on into definite integrals. Definite integrals are a lot easier, but they can also be tricky at the same time. So for this definite integral, we'll pull out 4, and then you will have the integral of square root of x, and you have your bounds of 4 and 0 dx. And by doing this, we'll have 4, and then we'll bound this to 4 to 0, and you'll have 2x in 3 over 2 over 3. it would be 3 over 2, but I just did the reciprocal of it and just move it to the numerator. By doing this, you will then have 8 x 3 over 2 over 3, and we're going to bound it by 4 and 0. Now, just by doing that, we can figure out the area underneath the curve. So in order to find the area underneath the curve, you take the higher bound minus the lower bound, or better known as the fundamental theorem of calculus. Minus 8, 0, 3 over 2 over 3, and the answer would be 64 over 3. That would be the area. And then we move on into this expression, which is very similar to the very first expression, but a lot easier. Pi over 2, 0. The derivative, or not the derivative, the integral of sine of x is negative cosine of x. So you will have negative 18 cosine of x bounded by pi over 2 to 0. And once you plug in pi over 2 at 0, your final answer will be 18. And then for the very last one, we'll pull out the 9. So then we will have 1 to 0, and then x in power of 8 minus, or 4 minus x in power of 9 dx. We'll multiply into x of 8, to the 4, and to the negative x in power 9. So we have 9, integral 1 over 0, 4 x in power of 8 minus x in power of 17. And just by doing this, we can find the integral of this. So 9 multiplied by 4x in power of 9 over 9 minus x in power of 18 over 18. And once you multiply this entire expression by 9, you can simplify it down to 4x in power of 9 minus x in power of 18 over 2. And once you bound it to 1 and 0, you will then have an answer that will be 7 over 2. So that's your definite integral. Then we move on into the fundamental theorem of calculus. So I'm not going to go into the basics of it, more so saying I'm not going to prove this entire theorem of the fundamental theorem of calculus. We're just going to be using what we're given and applying it into the functions that we have. So we're mainly going to be using the very first part in order to solve the integral. So what I'm trying to do here is I'm implying derivatives and integrals in order to cancel out so that you will get back your original function. So let's try that out. So in the very first expression, we can rewrite this entire function by d of dx, an integral of x in power of 3 over 9. And then you have this dp, which can be pulled out of here. So then 1 over p squared. So based on the fundamental theorem of calculus, it's kind of like the chain rule almost. You're basically integrating x in power of 3 into p, and then you're multiplying it by the derivative. So, and then you may be asking yourself, well, what happens to the 9? Well, if you do the derivative of 9, it cancels out. So you're taking the derivative of the upper and the lower bounds, and you're basically multiplying it at the very end. So your answer is going to be x in power of 3, all in power of 2, multiplying it by the derivative of x in power of 3, which is 3x squared. So you will have 3x squared all over, you will have 6x in power of 6, which can be also rewritten as 3 over x in power of 4. So, move on into this one. It's very similar, but we'll have it in respect to t. So, we'll integrate this here. That cancels for 0. So then our final expression would be sine of 3t plus 2, multiply it by the derivative of sine of t, which is cosine of t. And you're done. Now, this bonus one right here is a very difficult problem, but once you understand on how the differentiation and integration all works, it will be very simple. And we will also use L'Hopital's for the limits. So for the very first one, you can see we're given the fundamental theorem of calculus. But if it was upside down, say for example, if you had x in bottom and 3 in the top, what you will have to do is you will have to take the inverse of it. So it would be negative integral of x in power of 3. So that is a very important thing that I want to mention. Whenever anybody is doing calculus, don't forget that. It's very important. Know your upper and lower bounds. So in order to use or solve this problem, we have to use L'Hopital's. So we're just going to assume that the top and the bottom approaches 0 in the form of 0 to 0. So we take the derivative of the top and the bottom. You can see that the integral and the derivative will cancel out, but your x's would be replaced with the t's. So you will have e in power of 2x square root of x plus 1 all over the derivative of the bottom is 2x. And then you would have the limit of x approaches 3. So we don't have any other issues with this particular problem now, because we wouldn't have an undefined solution. So now we could just plug in 3 directly. So you would have e in power of 6 square root of 4, which is 2, and then 6. So you will have 2e in power of 6 over 6. So that is the same as e in power of 6 over 3. So that was a little bit of a tricky problem, but that is all I have for the fundamental theorem of calculus. And that is the last topic of Calculus 1. So I really hope you guys enjoyed this video. If you guys have any questions or concerns, please don't hesitate to leave a comment down below. Other than that, I'm calling it a day, and I'll see you guys in the next video.